Welcome to this Nordic Semiconductor webinar. Today we're going to talk about the exciting new nRF9160 features in nRF Connect SDK version 1.2. My name is Petter Myhre and I work as a product marketing manager for Nordic Semiconductor. And with me today I have Peter Rand, product manager for cellular IoT. Maybe you can say a few words about yourself, Peter.
Thank you, and thank you everyone for joining the webinar. So my team is responsible for the product definition of all the cellular products at Nordic, which includes the nRF9160 software and hardware. And look forward to giving an overview today of the product itself and some of the new features that we have in the SDK.
So then we have some practicalities. So this webinar will have approximately a duration of 50-60 minutes. Questions are encouraged, so please type in your questions in the top right sidebar. All questions are anonymous, but if you're using the chat, your name will be visible. We will answer questions towards the end, but if you have more questions, please use DevZone, where our application engineers is ready to answer your questions. A recording of the webinar will also be available after the webinar is over, together with the presentation at webinars.nordicsemi.com.
So today, in terms of content, we're going to go through an nRF9160 overview and architecture, and then we're going to look at some of the features and how they fit into that. So we have assisted GPS with the supple protocol. We have the cloud-assisted GPS with the nRF Connect for Cloud. Then the new options for updating firmware over the air, and serial LTE modem functionality, as well as an overview of the new carrier certifications. And then there will be plenty of time for Q&A at the end. So I always like to start with this slide. We set out with 3 specific goals in mind on the nRF9160 design. We set out with success to make the lowest power LTE-M and narrowband IoT chipset in the market. To achieve that, we built everything from scratch for low power without any of the legacy LTE overhead. We also applied techniques and know-how from our long history in low power wireless MCUs to design it. And that includes using integrated memories for execution to avoid loading over external pins, the executable memory. And we extensively use low leakage process features. Our second goal was to design a device for cellular that is as easy to use in an IoT development as the products that we have that employ the other wireless standards like BLE and Zigbee and Thread. So we put all the software tools and documentation online. We sell our development kits through all the major distributors, and we focus on building end-to-end examples and provide great support. We're not done with this one yet, but we have made great progress over the last year, and we have great plans for the future. The third goal was to achieve an unprecedented level of integration. We set out to make a complete communication and application module with all the relevant components included. And instead of using traditional PCB technology and a shield cam, we used chip packaging technology, or system in package, and some advanced plated shielding technology. And this resulted in a 10 by 16 by 1 millimeter product that fits in almost any end product use. So the nRF9160 is fully integrated, and it is unique in that it includes a low power embedded processor, a full modem, and all the associated memory on the same die. So when we put that together with a PMIC, some passives, crystals, and the RF front end into a system in package, it serves to pre-integrate almost everything you need for a low-power cellular IoT device. It remains for you to add your chosen battery, sensors, SIM card, and antenna. And those are application specific and depending on the region that you want to operate in. The application processor and modem share power management and clocks with automatic power management of power domains to ensure that the device stays in the lowest possible power state at all times during application and modem cycles. The nRF9160 is pre-certified as a module for global operation with one single SKU to support worldwide deployment, and that really plays into the promise of using a standard 3GPP technology for wide area connectivity in any part of the globe. Taking a dive into the application processor, which is what we're going to talk mostly about today. It is an ARM Cortex M33 from ARM at the core of it. It's the latest in low power processors, and very importantly, it features the ARM Trust Zone. Trust Zone is a hardware-based component for trusted execution. It is used for secure boot, for partitioning out software that handles encryption services, and it can be extended to further secure any piece of the code that handles critical functions from a security perspective. And this is a great tool to secure the devices from over-the-air attacks. The CryptoCell 310 is included as well, and that enables an additional layer of security at the application layer by performing computationally intensive crypto functions with minimal power consumption. So you can use that to add payload level encryption of data going over the air, or you can secure interfaces to external memories or processors. The application processor has a megabyte of onboard flash and 256 kilobytes of RAM for use by the application. We'll show more in a couple of slides what is going into that memory. And it also features a wide range of standard MCU peripherals and 32 GPIOs. Looking at the other side, the modem is a multi-mode LTE-M and narrowband IoT and GPS modem. The modem is its own secure island with a feature-rich interface to the processor. So we have a tight integration between the application processor and what it can control in the modem. The API gives access to switch between LTE-M and narrowband IoT depending on application needs or depending on network availability. And it also gives you access to GPS functionality. One of the things about the GPS that is very nice is that it is an advanced scheduler that handles the slotting of GPS operation in between the LTE cycles. So in EDRX and PSM, when the LTE radio is not active in talking to the base station, it automatically slots in the GPS operations you want to do. And that is not only something that allows for very efficient use of the hardware resources on chip, but it also automatically handles the coexistence between the two radios. So they're never actually active at the same time, and that eliminates the connectivity challenge, coexistence challenges between those two. You can even use the same antenna for LTE and GPS without any external switches. So the GPS frequencies fall right in between some of the LTE frequencies that are being used. And in some cases, depending on your antenna design, you can use the same antenna for LTE and GPS. The power consumption is the aspect of the device that I'm most excited about, and we have been able to achieve some very impressive numbers. That positively impacts battery life in a very meaningful way. And in idle EDRX, so staying connected with the network with a 1 minute 20-second interval, we're at 20 microamp current consumption. And that includes all the parameters being retained in low leakage RAMs to be able to stay fully connected to the network during sleep. So taking a higher level view again and looking more at the software aspects, a cellular device can connect to several devices or services in order to handle different aspects of operation. The application you make typically connects to your custom application in the cloud. The LWM2M device management with FODA and diagnostics typically connects to a device management service in the cloud, and then the SIM card, or eSIM depending, connects to the MNO or MVNO and their connectivity management platform. These platforms can also, of course, be integrated again in the cloud, or they can all be the same server, but the typical split is as shown here. On the nRF9160, the embedded firmware is split into two parts, running on the application processor and running on the modem. The application is what you develop with the SDK that we're going to talk about today, and includes the API that you talk to the modem with. So it has some communication protocols on top of the BSD sockets to the IP stack, and it has some management functions for the connectivity, and then of course, most importantly, the application that you develop yourself. On the modem side, the firmware is a certified and released binary from Nordic that handles all of the TLS and DTLS crypto. It handles TCP and UDP, the full IP stack, and the LTE stack, including all the SIM management functions in the LTE stack. The nRF Connect SDK is the software development framework for the nRF9160. It is built around the Zephyr RTOS from the Linux Foundation, and this is something that we continuously develop and improve to make it easier to piece together the elements that you need for your application. One of the ways we do that is by providing standard protocols and system features, but we also provide a number of examples showing how to make a fully featured asset tracker, a couple of ways to do FOTA, a cloud connector abstraction to enable connectivity to different clouds. We have a GPS example. We have an example of an LTE to BLE gateway, and several other samples that are found in the GitHub. The way that we manage the nRF Connect SDK is providing quarterly production releases that are tested and tagged by Nordic. So each nRF Connect SDK release is tested with the latest modem firmware. And meanwhile, features become available in GitHub as they become useful. So you will see those as pull requests before release, and you will also see our internal developers commenting to each other on the pull requests. And so it's a very open process. It's all open source. It's available in GitHub. And the big caveat is the releases are managed by Nordic. And that's how we get to a production level quality with a open source framework. Now I want to say a couple of words about the nRF Connect for Cloud. That is where the development kits connect to out of the box. So the nRF9160 DK or the Thingy 91 connects to the nrfcloud.com at boot up. That connection is using MQTT over TCP TLS with pre-provisioned credentials. nRF Connect for Cloud offers several features like SIM card management, data display, firmware updates over the air, and it even has a device API that allows you to extract data to display in a web page or load into your own database. And you do that using a token that you can get from the nrfcloud.com after you're logged in. So I encourage you to view the webinar that we put out on Thingy 91 in order to see some of the functionality here in action. And that's available on the same page as this webinar. So the first feature that I'm going to talk to you about today is the assisted GPS. That is a new feature in the 1.2 release that came out in February. So the GPS is, of course, a solution for downloading data from satellites in order to assess the position of the device. It leverages two main pieces of data. So one is the Almanac that is valid for several months. The other one is the ephemeris, which is valid for approximately 2 hours. Each one of these blocks of data need to be downloaded somehow. In the standard GPS operation, it's downloaded at a 50 bits per second link from the satellite. after you have a fix on one of the satellites. And low bandwidth impacts time to fix. So this is quite slow. So I also want to mention in this context that the sensitivity and time to first fix really improved in the modem firmware 1.1 release that we did back in November. And that is the modem firmware that the NCS 1.2 is tested with. So the numbers that we typically see now for a cold start, which is what we call when it's been off, sleeping for many days, typically a lot of the data in the Almanac ephemeris are invalid. We see a time to first fix of about 40 seconds. Then if you have a warm start, which is after a sleep cycle of a few hours, then your time to fix is about 20 seconds. And then once you have a hot start, which means all the data you have, Almanac and ephemeris, is valid from the last time you got a fix, the time to fix is about 10 seconds. Now we're going to look at what the assisted GPS functionality does to those numbers. So it improves the time to first fix and time to fix in the warm start scenario quite significantly. And it does that by, instead of using that 50 bit per second download from satellites to get the relevant and accurate data for satellite paths, it uses the 360 kilobits per second LTE-M link. And that brings the numbers down from a cold start, warm start, and hot start being three very different things from a timing perspective, to those all happening pretty much at the same speed. So it's less than 10 seconds to get a fix on all of those, regardless of how long it's been since you last slept. And the way that we do this is by getting the position of the local cell on the LTE network that you're connected to, uploading that cell ID to a server, and getting the relevant data for your general geographic area back. And there are two protocols that we offer to do this. One is the standard one, and that is the Secure User Plane Location, or SUPL. That's what's being used by cell phones. We have an example application and documentation in the SDK for that now, in the 1.2. There's a library in there for the core of the AGPS. It's binary, but it's free of charge. There's a cost to use this depending on the service agreement with the third party. So we use Google SOPL server for the example application, but SOPL is the standard protocol and supported by many service providers. So one of the challenges with SOPL is that it is not optimized for embedded devices or low power devices. So we saw the need to develop a more optimized protocol for cellular IoT. And we call that the nRF Cloud Assisted GPS. And that is a really significant step down in terms of the cost of data transfer. So we transfer less data. We greatly increase the battery life by reducing the amount of data that needs to be downloaded and how much processing needs to happen to it once it's on the device. And there's a reduced code overhead on the embedded side. More of the intelligence and processing is happening in the cloud. And since the cloud, in this case, is our nRF cloud, the application there knows exactly what data the modem in the nRF9160 needs to be efficient. So it's an assistance feature, but it's really optimized compared to the standard SOPL. The received location data is actually in the background coming from a third-party service. So what our cloud does is to repackage that data and format it in a way that is specific to the nRF9160. So that gives very fast download, very efficient parsing on the device. We have an experimental version of this that will become available in the GitHub, if it's not already, sometime this month. One of the other advantages here is that if you are using nRF Cloud for other services, you can reuse the same TLS credentials to keep the assistance functionality going on the GPS, as well as use the other services like FODA. The serial LTE modem is the next topic. When should you use a serial LTE modem? The nRF9160 has an integrated application processor, but in some cases it goes into systems where there are other processors around it. And what the nRF9160 provides then is a very flexible modem for use of an external application processor. So you connect and control over UART. You have interface device with the standard AT command set. And then you can customize and add functionality because you are simply using one of the examples in the SDK. And the addition of device management functionality, for example, that is specific to the carrier that you want to use, or your own device management, doesn't have to be a concern for the external processor at all. And you can add this functionality into the example, and then by that measure, build your own custom application processor interface and build your own custom functionality on the nRF9160. So it's useful in the following scenarios. So it's either for, we want to do a quick modem evaluation of the functionality of LTE, sending some UDP packets back and forth and connecting with different parameters. Or if you want to keep your existing application host and use the nRF9160 as a modem. And the third step that we see is that once you've done that, there's, of course, the opportunity to migrate code from the host onto the nRF9160 application processor and really save power and cost and potentially board space as well. So what do we have? The serial LTE modem application is in GitHub under that name. It consumes about 10% of application memory resources out of the box. Once you start adding functionality to it, of course, you will start consuming more of the memory. The serial LTE application resides then in the application processor, and the modem stays unchanged. That is the standard modem. And you then have your host application, which could be the nRF Connect link monitor, for example. You can find in the nRF Connect for desktop tools. So that is an easy way to do some evaluation of the LTE functionality on the device. In terms of roadmap, we currently support TCP client, UDP client, and of course modem and network control with AT commands, as well as power management and GPS functionality. Further out, we'll add to the serial interface an option to run a TCP server or a UDP server. And then in March, we'll add the assistance features for GPS into it, as well as the HTTP, HTTPS, MQTT, and CoAP protocols. The TLS client, DTLS client is coming towards April, and then the FTP client will be later this spring, less common. Next feature we're going to talk about is firmware over-the-air updates. This is really about cellular IoT device management and making sure that the device can have a long life cycle in the field and stay running and stay secure. Can potentially also deploy new features to existing products this way. So the remote management really is about reducing costs. Obviously, going around in the field, updating devices using a cable is costly and a nuisance. So what Nordic offers is an application and modem FOTA that is a coherent solution in the embedded SDK for updating both application and modem using the same interface. So in this scenario, the nRF Connect for Cloud is used for managing devices and firmware. This is really the control interface. We use MQTT simply because it runs well over the TLS connection that we have to nRF Connect for Cloud. But you can also change this to use LTE-M to M, which is also commonly used for device management. Once the modem decides that it needs to do an update, it will use HTML to download the new firmware image from a storage service. Of course, over secure HTTPS connection in that case. The application FOTA downloads a full new image and stores it in swap space. That can be either on chip or off chip. And it verifies and authenticates that image, checks signatures, then reboots to swap and replace the active application with the new one. On the modem side, things are a little bit more advanced. We have a differential FOTA approach. That leads to very small size updates, and the application transfers the image to the modem, or more like streams it. There's no need to store it in the application memory. And then the modem decrypts and authenticates the new image, checks it against the Nordic signatures, and then the modem reboots to apply those changes. So that is the general process. Few more words on the differential modem FOTA. So obviously the main motivation here is to reduce the size of the downloads, the cost on the data, and also the battery to do those downloads and the flash writes. So these are small differential images. So historically, so far we've seen them being in the 20 to 60 kilobyte size to go from one release on one branch to another release on the same branch. And the modem FOTA is really designed to fix bugs and security issues, and for a differential update, it's not designed to add new features or upgrade from one branch to another. So this is really to keep the devices in the field running stably with the same feature set. The FOTA implementation in the nRF Connect SDK is handled by the MCU Manager. It is an open source component with documentation. The default configuration uses nRF Connect for Cloud device management, and then it can also be changed, as I mentioned, to accommodate other needs. And there are a host of different device management systems out there. You may have to deal with one from one of the carriers that you want to certify with, or you may have your own, or there's some third-party suppliers of those things. So having a flexible way to connect to different device management solutions is really critical, and the nRF Connect SDK component there provides that functionality. So a few words on certification. We have leading worldwide coverage with one single SKU, as mentioned. There are mainly three components to the certifications that we do on a product like the nRF9160. At the final stage, it comes down to whether you want to certify with your local MNO, mobile network operator, and that generally has separate certification schemes for LTE-M and narrowband IoT. Then there are the mandatory regulatory standards that you need to comply with depending on the regions you want to deploy in. This is typically a CE, FCC, Industry Canada, those things. And then you have your 3GPP compliance certifications, which is either GCF or PTCRB. And which one of those you have to deal with depends on which carrier you want to certify with in the end. The nRF9160 is certified for both. There's a full overview of all the certifications we have on the nRF9160 on the link below, and that's continuously updated as we get more regions and more carriers certified. In terms of the regions supported, we have the countries in blue covered by regulatory certification on the nRF9160. The China is ongoing, and we're expecting that to complete in March. The bands that are involved in an LTE deployment in the different regions depend on how the carriers have rolled out their networks in those regions, and we support virtually every relevant band between 700 megahertz and 2.1 gigahertz. The carrier certifications that have been completed on the nRF9160 is the Verizon certification in the US. We have Vodafone that covers a large part of Europe and some of the other regions that Vodafone operate in. That certification is for narrowband IoT. The Deutsche Telekom was also recently added here. We have Germany, Austria, and a host of other countries supported on the Deutsche Telekom networks and affiliates. For Deutsche Telekom, we're certified for both NB-IoT and LTE-M as the first chipset and module to be certified for that. And we have several more in progress that will allow us to reach worldwide carrier certifications by 2020 end. Thank you. And now we will go through the questions.
Thank you, Peter. Thank you for that great presentation. So let's see if you have some questions here. So the first one is, in my country, NB-IoT is supported by VittleCop. If I use SIM or Vittel for nRF9160 DK, can I use Nordic Server or Google Cloud Platform?
Yeah, so for Viatel, the question is going to be if the use of TCP connections is allowed and if there's enough bandwidth for them to be stable. So generally, we recommend UDP with NB-IoT connections. And unfortunately, Google that you mentioned here and the solution that the nRF Cloud is based on do not support UDP connections directly yet. So that's going to be the question. Does the Viatel network give you enough bandwidth to maintain a stable TCP connection?
Is there any antenna design reference or guide how to design a good antenna of the nRF9160 LTE signal?
It's a good question. So we recommend using an antenna vendor and their services to figure out the exact radiated characteristics that you need. But for general recommendations on antenna interface to the nRF9160, there's a good white paper called the WP033 that is on the Nordic Info Center. And that has a lot of general and useful information about connecting antennas and the different options you have available.
Can the nRF Cloud be used in production with custom hardware?
Good question. So no, not as of yet. We exclusively use it with our own dev kits. And of course, you can use your own custom hardware there in the development phase. But for production, we do not yet have that service. And that's something that we're looking into providing.
Can you provide docs for the IPC subsystem, or are we restricted to using the proprietary C library?
For now, we only distribute the BSD library that interfaces to the IPC as a binary. We have plans to make that open source in the future, but it's a complex machinery.
Will the proprietary C library support sending raw IP packets if we want to run our own TCP IP stack on the application core?
Yeah, it actually supports raw sockets. So please check out the documentation that you find in the nRF Connect SDK documentation. And there you'll see raw sockets listed as one of the available features.
When will the proprietary C library support TLS 1.3? How about HTTP 3 over QIEC?
Yeah, so Quick certainly looks interesting, especially for the kind of devices that the nRF9160 is well suited for. Unfortunately, it's not supported by many cloud services yet. I think most everyone's using just the one that does. We haven't had a lot of requests yet, and that goes for the TLS 1.3 as well. But we certainly aim to keep our ciphers updated with the relevant new TLS releases.
Can the nRF9160 act as a TCP server in an NB-IoT connection to the base station? Is there an example?
So maybe split this in two. So can the nRF9160 act as a TCP server? Yes. And I think you saw that in the roadmap slides for the serial modem. Over NB-IoT, again, you're going to have a little bit of a challenge running a TCP server in some of the NB-IoT networks, just because NB-IoT uses the control plane for data. And it's not always recommended to keep a TCP, especially with TLS, socket open and try to maintain that over those, let's say, not guaranteed throughput and latency connections that you get.
What about HTTPS secured support?
Yeah, that's in there. That's supported. So you simply pass the TLS credentials to the modem. Then you can not read them out again, but you get a handle to those TLS credentials. You can use those to open a secure TCP socket on the BSD interface, and then you just run HTTP over it. I believe there's an example in the SDK.
Is there a connector for current measurements and current profile?
Yes, there are hooks for current measurements on the nRF9160 DK. And of course, given our good performance on power, I really recommend everyone to take a look.
When will the nRF Connect SDK toolchain manager app for nRF Connect for desktop, shown in Tuesday Cellular's webinar, be available?
Yeah, thanks for asking that. I mean, that for us represents a pretty significant step up in terms of ease of installing the tools. So we're pushing to get that out as soon as possible. The target date now is mid-March. I think that will happen.
Is there any plans to support development in Visual Studio environment like the Visual Studio Code?
Yeah, it's my personal favorite. Some of our engineers use that today, and we're looking into building better support for it. But we still have work to do to get Segar up and running, and that's priority one right now.
Is there any example using MQTT and AVS?
Yeah, there's actually a very comprehensive one. It's called the AWS FODA. That's in the sample application folder in the nRF Connect SDK. There's actually a couple of others that use the MQTT and AWS as well. So yeah, check those out.
Can you update major version modem firmware from the cloud?
Yes, you can. The caveat is then you need some external swap memory to store that full image for the modem. It's somewhere around 2.5 megabytes. And of course, then you also need the battery and the data plan to support that download. So, but yes, that is a possibility, and it's something that some of our customers are putting into place.
There's a bug with Segar Embedded Studio debugging starting from the version 1.2 tag. Do you work on resolving that? Currently, if you have to debug and add some BLE functionality, if you have to merge USB UART bridge example with our code.
We are painfully aware of two critical issues with the recent release with respect to the Segger compatibility, and we are working very hard with Segger to resolve those as quickly as possible.
Is modem binary firmware upgradable in a safe way?
Yes, several measures have been put into place to make it safe, and by that, survive sudden resets during update, for example. From a security perspective, we sign and encrypt all new firmware images. But yeah, this is more about safety, and that's handled by a process internally in the modem.
How often can we expect firmware updates?
So the modem firmware will be released around once every 6 months. Those are mainly now tied to release of new functionality for new carrier certifications. And then we also have new examples that come with the NCS releases, and the NCS releases are once per quarter.
Shielding is not necessary anymore, is it?
That's correct. So the system in package module that is the nRF9160 is shielded with microplating. So you don't need a shield can around it.
We have tried to use the GPS on Thingy 91 and found it was weak, especially inside a car. Would a GPS improve this?
Yes, it would improve it to a certain extent. Unfortunately, from a antenna design perspective, the the Thingy 91 is not a really good example, and we are aware, and we're actually working on an updated design of the Thingy 91.
Is there any nRF91 LTE GPS antenna design reference guide? Can LTE and GPS antenna use one antenna or needs two antennas? Does nRF9160 support SMS and voice?
Right. So for the antenna questions, those are both answered in that white paper 033. So please check that out. So you can use one antenna for both LTE and GPS, or you can use one for LTE and one for GPS. Regarding SMS and voice, the nRF9160 is really a machine-to-machine kind of device. It does support SMS. That is very useful in some scenarios. It does not support voice.
Is there a way to improve GPS accuracy, like RTK?
We do not support RTK.
Is the Almanac update automatic or manual? Does it have to be triggered by the user?
No, that's automatic. The modem requests the updated Almanac from assistance if it needs it, or it downloads it automatically from the satellites if you're not using a GPS.
Can assisted GPS be used on NB-IoT network?
Great question. So no, not right now, but because supple will not run over NB-IoT. Again, back to this TCP question. So one of the goals of the optimized solution that we have with cloud-assisted GPS is to be able to run that from the nRF cloud over NB-IoT networks as well using UDP.
We heard during the Thingy 91 webinar that there will be a new version of hardware with better GPS reception. Can you please tell us when this new version will be available?
Yeah, that version is still in design. And given that we do a full end product certification on it, including CE, FCC, some carrier certifications, and we expect that this will take some time, and we'll probably have it in the market sometime around this summer.
Is it possible to use an approximate location provided by a third party, like an operator carrier, as an AGPS location to improve GPS TDAF?
Yes, that's actually part of the AGPS functionality. So the cell ID of the connected cell is used to get the rough position. So you upload the cell ID to the supple server. Supple server uses it to find your rough location. And that only needs to be accurate to around 100 kilometers or so, because you see pretty much the same view of the sky within that sort of area.
Now it is default iBasis SIM. it seems to have some limit, not supporting PSM mode with local telecommunications. How to develop a universal with different network?
Yeah, so the roaming agreements are continuously evolving for LTE-M and now also for narrowband IoT, and we're working hard with the carriers to improve coverage. There's challenges regarding PSM mode not being available in all regions, and there's actually a good blog on that written by iBasis that's on our DevZone blog. So you can go check that out to understand a little bit more of the background.
It can happen that some of the local providers does not allow roaming SIM cards to enter PSM mode. Is this limiting the use of iBasis SIM cards for getting GPS fixes? What kind of local SIM cards should we buy to benefit from PSM mode?
Yeah, that's a great question, because that really is at the heart of this. Some of the operators, the MNOs today, restrict access to PSM mode to SIM cards that are in their own MC ranges. And so you'll not get those, let's say, low power functionality when you use a roaming SIM card. So that restricts two things. One is you will not get low power operation, which means any sort of hope of long battery life will not work. And at the same time, you will not ever have time to do a GPS fix, because the radio will be active all the time on the cellular network, much like your phone is. So that's important then, to get a local SIM card that is within that MC range, or a SIM card from someone who has a roaming agreement that includes access for LTE-M and narrowband IoT over PSM. But the local cards, you can get any IoT local card will work.
Is the nRF Cloud open source project, meaning that would be possible to use it as a base for own proprietary cloud service for the Nordic nRF9160?
No, it's not. It's actually something that we aim to make a product out of.
I would like to use another MQTT broker, hence not the nRF Cloud and tool, to publish my data. Could I still implement the assisted GPS features?
Yes, absolutely. In that case, you can use the supple library and then have it point to a third-party provider like Google, and get the supple data from there, and then publish your data to your own cloud with a separate TCP TLS connection.
Then we have one last question, and that is nRF9160 currently in mass production?
Yes, it is, and it has been since last summer.
That's what we have time for today. Thank you, Peder, for the presentation and answering the questions in such a great way. If you didn't get an answer to your question, please go to DevZone and ask there. And we will make a recording of this webinar public shortly, so you can watch it again. We will also share the presentation. Thank you for listening.
Thank you.